You're interacting with machine learning dozens, maybe even hundreds of times a day. It's the magic behind your Netflix recommendations, it's the reason your inbox isn't totally swamped with spam, and it's even starting to make life or death decisions in fields like medicine. But behind all the hype and the buzzwords, there's a surprising amount of, well, art. So how does it really work?
Well, here's the secret that most textbooks are not going to tell you. Beyond all the complex math and the algorithms, there's this layer of practical wisdom, this folk knowledge that experienced people in the field really rely on. And honestly, getting a handle on this is what separates a project that totally changes the game from one that's just a frustrating failure.
So, what is this black art? What are the essential lessons and hidden traps that can make or break a machine learning project? Well, that's exactly what we're going to try to uncover here.
Okay, before we get to the really juicy secrets, we need to build a solid foundation. Let's just cut through all the hype for a second and get to the core of what we're actually talking about when we say machine learning.
At its heart, it's a really simple but profound idea. Think about it like teaching a kid how to spot a cat. You don't give them a giant checklist, right? You don't say, if it has pointy ears and whiskers and a long tail. No, you just show them a bunch of pictures of cats. And from those examples, they start to learn, to generalize, so they can spot a cat they've never ever seen before. That's the whole goal here.
So you've probably heard this dizzying list of terms: neural networks, decision trees, support vector machines. I mean, it sounds incredibly complicated. But what if I told you that every single one of those is really just a different mix of the same three basic ingredients?
Seriously, think of it like building with Legos. First, you've got representation. This is basically asking, what kind of blocks can I even use? Are they simple bricks or are they complex gears? Second, there's evaluation. How do you know if you're building something good? This is your scoring function. And third, you have optimization. What's your strategy for finding the absolute best way to put those blocks together? Do you just try things at random, or do you have a smarter plan?
And this table here kind of shows how that works in the real world. You can mix and match these components. So, for example, a decision tree, which represents what it knows, like a big flowchart of if-then questions, it might use a scoring function called information gain to figure out which questions are the most useful to ask. But another algorithm might use a totally different set of tools. All the variety and all the magic really just comes from these different combinations.
Okay, now we are getting to the absolute core of machine learning. See, it's not about memorizing the data you've already seen. It's all about making accurate predictions about the future, about data you have not seen. And this, right here, is where the single most common and dangerous trap is just waiting for you.
The main point is this. Getting a 100% on a practice test is actually pretty easy if you just memorize the answers. But that doesn't mean you've learned a thing. The real test, the only one that actually matters, is how well you do on the final exam, with questions you've never encountered before. That ability to make that leap is called generalization.
And this brings us to the main villain of our story: overfitting. This is what happens when your model doesn't just learn the material for the test, it memorizes every single little detail about the practice questions, including like the typos and the random coffee stands on the page. It completely fails to grasp the real underlying pattern. So this whole thing is a constant balancing act. On one side of the scale, you've got high bias, which is also called underfitting. This is a model that's just way too simple. It's always learning the same wrong thing, like trying to draw a straight line through a really curvy set of dots. And on the other side, you've got high variance, or overfitting. This model is way too complex. It's chaotic. It learns all the random noise in your data. The entire game is finding that perfect sweet spot right in the middle.
But even if you master that balancing act, there are these deeper, almost stranger problems that are just lurking in the data itself, and practitioners call them curses for a very good reason.
This quote, it points to a really deep truth in machine learning, and it's formalized in something called the no free lunch theorem. It basically says that no single algorithm is the best for every single problem out there. Without making some basic assumptions about your data, any learner is really no better than just random guessing. You simply cannot learn something from nothing.
And then there is this monster, the curse of dimensionality. Now, intuitively, you'd think that more features, more columns in your spreadsheet, that would always be better. But it is a trap. Imagine you're looking for a friend in a small town. Pretty easy. Now imagine looking for them in a 3D city with 1,000 floors. A lot harder. Okay, now imagine searching in a 100-dimensional space. The volume of that space becomes so ridiculously vast that your data points are like these tiny, isolated galaxies, and the very idea of 2 points being close or similar just becomes meaningless.
To put that into perspective, let's say you have 100 features, and each one can just be on or off. Even if you have a training set with 1 trillion examples, which is a huge amount, you've only seen about 10 to the power of -18 of all the possible combinations. That is an infinitesimally small fraction of the entire universe of possibilities. Your data, for all practical purposes, is empty. That's the curse of dimensionality.
Okay, so we've seen the traps, we've seen the curses. How in the world do successful practitioners actually navigate all this? Let's get back to that so-called black art.
This is one of the most famous sayings in the entire field. A lot of the time, the best path to a better result isn't some super complex new algorithm, it's just more data. Why? Well, because a massive amount of data can help even a simple algorithm cut through the noise and find the real patterns.
But hang on a second. While more data is great, the source we're looking at argues there's something that's actually even more critical. The single most important factor in a project's success is not the algorithm, and it's not even the amount of data. It's the features you design from that data. And this is called feature engineering. It's the art of using your human expertise, your creativity, to craft the right inputs for the algorithm. So for instance, instead of just feeding a model raw dates, you might engineer new features like, is it a weekday, or is this a holiday? It's this amazing mix of science and intuition, and it's often where the real breakthroughs actually happen.
And here's another powerful trick from the toolkit. Instead of spending all your time trying to find one single, perfect model, it's often way better to just train many different models and then have them all vote on the final answer. This is called an ensemble, and it's a standard technique for winning competitions and building the absolute best systems. All right, finally, let's look at one last piece of practical wisdom here, and it's one that challenges one of our most deeply held beliefs about simplicity. This is going to lead us to the ultimate question of what machine learning can do and, maybe more importantly, what it can't.
We've all heard of Occam's razor, right? For a long time in machine learning, this was treated like gospel. If you have 2 models that perform the same on your training data, you should always choose the simpler one because it will generalize better. Makes sense.
But it turns out it's not that simple. As we just saw with those ensembles, combining many complex models often generalizes better than one simple one. The really surprising truth is that in modern machine learning, more complexity can sometimes be your friend. Simpler is not always better.
In all of this, the balancing act, the curses, the debate between simple and complex, it leaves us with one final and really critical question. Machine learning models are absolute masters at finding complex correlations in data. They can predict what is going to happen with incredible accuracy, but they don't understand causation. They have no idea why it happens. And maybe that's the ultimate black art, the human wisdom to take a powerful prediction and know how to actually use it to guide our actions in the real world.